In this lecture, we're going to go over compressors and pumps. Compressors and pumps are devices in which work is done on a substance flowing through them in order to change the state of the substance. Typically, it's to increase the pressure and/or elevation. The term compressor is used for gases, and the term pump is used for liquids. For control volume and closing a compressor, the mass and energy balances at steady state reduced to the same as for a turbine. So we have our heat transfer minus our work plus our change in enthalpy is equal to 0. And much like with a turbine, the heat transfer is typically neglected. So we get our work is equal to our change in mass flow rate. This is not 100% true for pumps, since pumps are used to increase the elevation. So pumps often have changes in potential energy remaining in their energy balance. So we're going to do an example for a compressor. We have air entering a compressor operating at steady state at a pressure of 1 bar and a temperature of 290 Kelvin and a velocity of 6 meters per second through an inlet with an area of 0.1 meters squared. At the exit, the pressure is 7 bar, the temperature is 450 Kelvin, and the velocity is 2 meters per second. Heat transfer from the compressor to its surroundings occurs at a rate of 180 kilojoules per minute. Employing the ideal gas model for air, we're going to calculate the power input to the compressor. So our energy balance in this case is going to reduce down to our heat transfer minus our work plus our change in kinetic plus our change in potential. We can ignore potential energy changes. We're not going to ignore kinetic energy changes, as the problem gives us an initial and final velocity. So our work is equal to our heat transfer rate plus our mass flow rate times our enthalpy change plus our change in kinetic energy. We need our mass flow rate, which is our area times our velocity over a specific volume. And since this is an ideal gas, we're going to employ the ideal gas law and get that our mass flow rate is equal to our area times our velocity times our pressure divided by R and our temperature, which is 0.1 meters squared times 6 meters per second times 1 bar divided by 8,314 joules per 28.97 kilogram Kelvin times 290 Kelvin equals 0.72 kilograms per second. So our work is equal to the minus 180 kilojoules per minute times 1 minute is 60 seconds plus 0.72 kilograms per second times 290.16 minus 451.8, where these values come from table A22, plus 6 squared minus 2 squared times 1 Newton over meter second squared. Our work is equal to minus 119.4 kilowatts. Now we're going to look at an example for a pump. A pump at steady state draws water from a pond, a volumetric flow rate of 220 gallons per minute, through a pipe having a 5-inch diameter inlet. The water is delivered through a hose terminated by a converging nozzle. The nozzle has an exit diameter of 1 inch and is located 35 feet above the pipe inlet. Water enters at 7 degrees Fahrenheit and 14 psi and exits with no significant change in the temperature or pressure. The magnitude of the rate of heat transfer from the pump to the surroundings is 5%. The power of 5% power input. We're given the acceleration of gravity, and we're tasked with determining the velocity of the water at the inlet and the exit and the power required by the pump. To get the velocity of the inlets, we're going to use the fact that our mass flow rate is equal to our area times our velocity over our specific volume. To get our specific volume, we're going to fix state 1. It is liquid water, so our specific volume is approximately our saturated liquid specific volume at our given temperature, which is 0.01605 cubic feet per pound. So our mass flow rate is equal to 220 gallon per minute divided by our specific volume of 0.01605 cubic feet per pound. I'm going to correct my units. And I'm going to get my mass flow rate is equal to 30.54 pounds per second. I'm going to have our velocity is equal to our mass flow rate times our specific volume divided by our area, which is 30.54 pounds per second times 0.01605 feet cubed per pound divided by pi over 4, 5/12 squared. We get our velocity is 3.59 feet per second. For state 2, we have our specific volume at state 2 is equal to our specific volume at state 1, since we were told that the temperature and pressure between the inlet and the outlet does not change significantly. So our velocity at the exit is equal to our mass flow rate times our specific volume over our new area, which is 30.54 pounds per second times 0.01605 feet cubed per pound divided by pi over 4. We get our new velocity is 89.87 feet per second. Now we're going to figure out the work required by the pump using our energy balance. We have 0 equals Q minus W plus our mass flow rate times our change in enthalpy plus our change in kinetic plus our change in potential. And we're going to note that Q is equal to 0.05 W. So our work is equal to our mass flow rate divided by 0.95 times our change in enthalpy plus our change in kinetic plus our change in potential, which is equal to, since we're using liquid, since it's liquid water, and T2 is equal to T1 and P2 is equal to P1, H1 minus H2 is going to go to 0. So we have our change in kinetic energy is 3.59 squared minus 89.87 squared divided by 2, this is speed squared per second squared, times 1 BTU, 778 foot-pounds, times 1 pound force is 32.2 pound mass feet per second squared. Our change in kinetic energy is minus 0.1614 BTU per pound. We'll look at our change in potential energy, which is equal to 32.2 feet per second squared times our change in elevation times 1 BTU again, 1 pound force is 32.2 feet per second squared pound mass. Our potential energy change is equal to minus 0.0450 BTU per pound. So our work is equal to 30.54 pounds per second divided by 0.95 times 0 minus 0.1614 minus 0.0450 equals minus 6.64 BTUs per second, which is equal to minus 9.4 horsepower. In our next lecture, we are going to go over heat exchangers.